we can represent cosine x. So cosine x is 2 cosine squared x over 2 minus 1. That is 2 over 1 plus tan squared x over 2 minus 1, or if we take common denominator, 1 minus tan squared x over 2, 1 plus tan squared x over 2, that is 1 minus t squared over 1 plus t squared. So, in this way, we obtain the representation for every appearance of x in R. But also we have dx. So what is dx? We can represent x equals to 2 arctan t. So dx derivative is 2 over 1 plus t squared dt. So you see that after using all those substitutions, all those expressions, but to say substitution is only one, we obtain integral r of sine is 2t over 1 plus t squared, 1 minus t squared over 1 plus t squared, and 2 over 1 plus t squared dt. So we have a rational function of t, and it means after that we'll be able to find a primitive as a function of t. But as you see, if r is a function of some degree, then it will be a function, rational function of degree will be twice times degree of r, and also maybe plus 2, so very large degree of r will be after that substitution. That is why there are some particular cases when it's better to avoid this substitution and to use other possibilities. So, particular cases. So you see, each of those cases can be integrated using the same universal substitution. But this is not a very good idea because of huge expressions after substitutions. So particular cases. First, integral r of sine squared x cosine squared x dx. So it means this happens when we have some kind of evenness, right? In fact, it means that, roughly speaking here, if you substitute instead of sine x and cosine x minus sine x and minus cosine x, the function doesn't change. That is one way. In particular, this case also is here, but it's better to explain in this way. So, how to compute this integral? Look, we can substitute then tan x equals to t. Not tan x over 2, but just tan x. Why it works? Because now we can represent immediately cosine squared x is 1 over 1 plus tan squared x, that is 1 over 1 plus t squared. Sine squared x is 1 minus cosine squared 1 minus 1 over 1 plus t squared 1 minus t squared over 1 plus t squared. And lastly, dx, okay, x is arc tan t, dx is dt over 1 plus t squared. So, after that substitution, we obtain integral of rational function 1 over 1 plus t, 1 minus t squared, 1 plus t squared, 1 over 1 plus t squared, dt over 1 plus t squared. From the first glance, it seems practically no difference with this, right? But remember, this rational function is practically of the same degree as that one, because here we had square, right? So it means we had a rational function of sine and cosine of twice degree of r, and same degree will be here. That means we win a little bit in degree. And also this case in fact works if we have in general that one. So it's okay. So that's equivalent. If your function has such a property, then it can be represented as a function. Okay, let me use another. If you have a rational function which has this property, then it can be represented as a rational function of sine squared and cosine squared. That is equivalent. But sometimes this is better. Sometimes this is better to check. Okay? For example, let's say sine x cosine x over sine squared, 2 sine squared plus cosine squared. You see, this is not a function of this form from the first glance, right? It seems slightly different. But in fact, this is the function of that form. Why? Because if you check by this way, it works, right? Substitute. Instead of sine and cosine minus cosine. Two minuses, they cancel each other. So this property is satisfied, right? And you don't see immediately that this is a rational function of this form. But that's true. Why? Divide by cosine squared, both numerator and denominator. Then, what happens with numerator? You have sine x only, right? After division. And cosine will be, yeah, it will be a function of another possibility also when this works, integral r of tan x, right, dx. That is also is integrated by this way, right? And this function is an example. If you divide by cosine squared, then you obtain a function of tan x. So also works this substitution, but it can be seen immediately, right, from that, and just substitute tan x. Next particular case is for I'll collect together two particular cases. Integral r of sine x cosine squared x cosine x dx, and integral r of cosine x sine squared x sine x dx. Those integrals, again, r is a rational function, can be computed with the help of substitution. So just put cosine into differential. So it means for the first integral we use substitution sine x equals to t. For the second, cosine x equals to u, let's say, right? And after that, what we'll obtain? Cosine x dx equals to dt. Cosine squared x equals to 1 minus t squared. Sine x equals to t. So integral will be equal r of t 1 minus t squared dt. Here it's analogous, so sine x dx equals to minus du. Sine squared x is 1 minus u squared, and after that this will be integral r of u 1 minus u squared du, but with minus. And this also, like here, right? Like here, when it works, it can be represented with, so you can represent your function r1 in this form if r1 of, let's say, yeah, here if you substitute minus cosine sine, then you have minus r1 of cosine sine. Roughly speaking, the function should be odd with respect to cosine, like here it is written explicitly. Analogously, in that case, r1 can be represented in that form, here in that form, if r1 of minus sine x cosine x is minus r1 of sine x cosine x. So these are main cases of integration when we can find primitives in terms of elementary functions. Okay, so we finish the chapter about indefinite integrals and we start next chapter. So I'll erase now everything. May I erase? Okay. Okay. So, chapter 2. Chapter 2, integration. And first section, so for this lecture it will be 6.2. Definition of the Riemann integral. And I will start with some informal ideas. So, integral, you see, there were two concepts of integral, and one was integration like an inverse operation with respect to differentiation, that is indefinite integral. You have a derivative, you want to find a function which has this derivative. So inverse operation to differentiation. That is one understanding of integration. Another understanding, integral is an area. And most wonderful thing was that those two seemingly completely different things are the same. You see, one, integration is an operation which is inverse to differentiation, right? You differentiate, you want to find inversely the function which was differentiated, right? And it turns out that if you want to find an area, it is again integration. And that was completely unexpected, and this was really discovered. And also it explains the sign of integration. What is sign of integration? That is similar to summation effect. So you make it smoother, right? And in fact, that is in analogy like you have finite sum, that is discrete sum, right? So 1, 2, 3, and so on, right? Finitely many terms, right? And then you make this sum smoother. It means you have infinitely many, but not infinitely many, not countably many, but uncountably many summands, uncountably many terms. Of course, it seems very strange. What means uncountably many terms? How you can sum them? And so those signs, they are related to each other. So this sign was generated by that one. And now we'll start with formal definition. So how? We want to define an area, and we start with an area under the graph of a function. Of course, non-negative function, otherwise makes no sense to represent like an area. So we have non-negative function, y equals to f of x. And we are interested in understanding what is area on this graph. Okay, the simplest idea is to replace this figure, I mean we are interested in the area under the graph, right? This trapezoidal figure. And the idea is to approximate this figure by figures with easily computed areas, right? And which are the simplest figures? Rectangles, right? From the point of view of area, which figure has the simplest formula for its area? Definitely it's rectangle, right? So we want to approximate this figure with the help of rectangles. How? The idea is the following. So we take small intervals, we split our interval AB into small intervals, and we approximate. So you see, if we split our figure, I mean our trapezoidal area, if we split our figure, we obtain again small trapezoidal figures, right? And from the first glance, nothing is better than was before. Because again, how to compute even those small figures, areas of those small figures. And the idea was, okay, if this is very thin, right, then we can forget about this slope and so on. We can think about the top of this figure as a horizontal line, right? But next question, which horizontal line? There is a choice, right? We can choose maximum, we can choose minimum if it exists, of course, right? But in general, we can take arbitrary value of our function somewhere between, right? And that is most general idea. So what we do? We replace every small trapezoidal figure by a rectangle. And okay, we can expect that if every length is sufficiently small, right, then if we add all those areas, I mean small areas, right, we have many, many rectangles after this operation, right? We have many rectangles. We can easily compute area of each of those rectangles, right? We add all of them together, right? And we have an area of a figure which seems to be very close to our trapezoidal, right? So somehow we need to understand what means close, what means approximate, and so on. We have operation of limit, right? So we take a limit, but look, there are many, many different variables here. First of all, we split into those pieces, right? Variable. Every of them is a variable, right? Next, we choose a point. where we take value of our function. Even more variables. So many variables. And that gives a necessity to introduce new definition. So I'll start with this definition. A partition P of the interval AB is a collection of points x1 so on xn minus 1 such that A equals to x naught, by definition x naught is less than x1 so on less than xn minus 1 less than xn, which is by definition is B. So you see, the very first point x naught is A, the very last xn is B. Other points are chosen arbitrarily, like on our picture. So that is x naught, x1, x2, so on, xn. So that is partition. There is a first variable, in fact not one variable but many variables, right? Moreover, even number of variables vary. We don't fix this n, because if we want to have small and smaller n's, right, then we need to have more and more points of this partition, right? If we want those intervals to be very small. But what means very small? We have many intervals. So next notation, delta xi is by definition xi minus xi minus 1, I1 up to n. So what is delta xi? For example, delta x1 is here. Delta x1 is the length, delta x2, right? Delta x2. Delta x2 is the length of the interval x1, x2. No, there is a question uncountably many terms. Finitely many terms, even not countably many terms, only finitely many terms. At the moment we have only finitely many terms. That is, I understand why this question appears. This question appears because of my discussion with respect to sines, right? But at the moment we have only finitely many terms. That is. Okay. Next. So, at the moment we know everything with respect to those points, but still there is a necessity in discussing what means small lengths, right? We have many different, right? Nobody asks about equidistant points. They need not to be equidistant. Arbitrary. Just arbitrary. So, next definition, norm or mesh of the partition and partition I'll denote just by this So partition will be denoted by listing all points. Is maximum of delta xi for I from 1 to n. And okay, forget about notation which is used in your lecture notes. By the way, I don't know what will be in future, but for a while it seems lecture notes are very, very close to Zorich book. No notation. Okay, no notation. Just norm is this one, nothing else. So now we have some measure to measure what means small intervals. So you see, we have finitely many points, right? So we have finitely many, in general, different lengths, maybe equal, doesn't matter. And we take maximum of all those small lengths, right? And that is called norm or mesh of the partition. Okay, so now everything is defined what is related to x-axis. Now let's start to discuss y-axis. So we choose a value. That point is, let it be xi, okay, here it's third interval, so xi 3. So definition. Target partition P xi is a partition P, okay, let me list all points in that partition together with distinguished points. Xi I x I minus 1 less or equal xi I less or equal x I. I from 1 up to n. So xi I belongs to that interval I from 1 up to n. Look, so what means target partition? Target partition means that we take a choice of points which split our interval AB together with distinguished points where we'll take a value of our function. Now everything is defined. Okay, let's have a break. I think I need to denote norm somehow, so let it be lambda of p. Lambda of p be the norm of mesh. Okay, now let us write down what I described before. I mean, what is the area of that strange figure which consists of those very thin rectangles? right? So we take many thin rectangles, take their areas and add them together. What we obtain? Let me write down what we obtain. We obtain sum of n terms according to how many intervals we choose, right? And for each term, what is area of one rectangle? What we need to do? We need to multiply the length of one interval. What is the length? Delta xi, right? That is the length of one interval times the height. What is the height? We took value of our function at the distinguished point. So f of xi I. That is the area, right, of this figure which approximates our trapezoidal figure, right? And that is called integral sum. So definition: Riemann, sometimes we'll omit that this is Riemann integral sum, for a function f is as f p psi equals to the sum f of psi I delta xi for a target partition p psi. So once we choose a target partition, and let me recall once again what means target partition. We choose splitting of our interval, right, for the basis of those small rectangles, right? And then we choose a point, a distinguished point on each of those bases to determine the height of our rectangle, right? That is the idea. So that is Riemann integral sum. Now, what is to approximate? It means we need to take a limit, right? And that is also a difficult thing, because you see, we have so many variables. We have variables xi, we have variable n, number of points, right? And also we have variables psi. So we have many variables. And we know only a limit of a function of one variable, right? But what we can do, we can write down the definition which is can be defined rigorously And maybe I'll do it a little bit later. But firstly, I want to proceed without this rigorous definition, a special limit. So let me give the following definition. So, definition. We say I equals to limit as lambda of p tends to 0 of integral sums if for arbitrary epsilon greater than 0 there exists delta greater than 0. So look how I want to construct this definition. I wrote here limit of something as norm of the partition tends to 0. Norm of partition is one variable, right? So for one variable we know what is limit. So I want to write down what is it. For arbitrary epsilon greater than 0, there exists delta greater than 0, such that for every partition P with norm less than delta, but remember that integral sum also has distinguished points inside, right? So we insert here also for arbitrary distinguished points psi I belongs to xi minus 1 xi I from 1 up to n, right? We have the inequality which is quite similar for usual limit. So at the moment I don't want to give you rigorous definition of a limit on a base. Maybe later I'll do it. For a while I want to construct it similarly to usual limit of a function. So look, when we consider target partition we have many variables, but we replace all of them just by one, norm of partition. Once we estimate norm of partition, everything else, I mean P and Xi, is arbitrary. The only thing which we should estimate is the norm of the partition. So what it means? It means that what we want to have a limit independently on how we choose those points and so on. The only thing which is interesting for us is maximum of those lengths. That's all. There is a question. F of Xi, right? What is f of Xi? If that is Xi, then this is precisely f of Xi3. I didn't indicate it, but of course I should do it. Thanks for that question, right? So that is height. So the question was, is f of Xi is a point or height? Both. Point and height, right? Oh, minimum is not logical, sorry. Minimum is not logical. The point is maximum should be small. If maximum is small, then definitely minimum is also small. Otherwise it might be, look, if you are interested only in smallest, then what can happen? You take here smallest, right? And very large. Definitely it will not approximate, right? If you take such a huge rectangle, right? It doesn't approximate good our area. Okay? Okay. So, that is what we understand under this expression. Limit as, and we read it as usually. Limit as norm of partition P tends to 0 of the integral sum. And now, next definition. The Riemann integral of a function f over interval AB is the limit of integral sums if it exists. Of course, finite is the finite. Let me insert here finite to avoid infinite integrals in the moment. The finite limit of integral sums, if it exists, of course. That is very important thing, if it exists or not. So, and I'll start with very natural, necessary condition. So, okay. Maybe it's better to discuss more the definition. So, okay, I said that I'll give you a rigorous definition of what means this limit. I mean, I gave rigorous definition. Everything is very rigorous with quantifiers, so it's very rigorous definition. But maybe it's good idea to give a general scheme which explains how we can put it in the same form as usual limit of a function. So for a while, what I want to talk about now is not about Riemann integral. That is about this limit. So now I want to discuss the notion of this limit in more details with the help of limit on a base. So let me start with definition of the base. Definition. A base B okay, I think of subsets B in X is a collection of non-empty subsets B in X such that for any B1 and B2 in B, B1 in B, B2 in B, there exists B in B such that B is a subset of the intersection. So let me give first example of a base which is related to the definition of usual limit of a function. So example 1. The collection of okay, B is the collection of punctured neighborhoods 0 less than x minus a less than delta for all delta positive. That is a base. Why? Because if, let's say, B1 belongs to B, B2 belongs to B, then what it means? It means that B1 is I would put here this. So B consists of neighborhoods. This one is a neighborhood, right? Here I choose axis. Okay, let me write down. It's not. Is it 0 less than? Otherwise, it's not clear, right? Where is x such that 0 less than x minus a less than delta, where delta are positive. So you see, B consists of neighborhoods. Clear? We take the set, the collection of neighborhoods. So B1 is 0 less x minus a less than delta 1. B2 is the set of less than delta 2. Then, what is the intersection? The intersection is a punctured neighborhood which can be characterized just by that one. Okay? So, and that is precisely B, which is also belongs to B, the collection B. So, this is a base of subsets of real Y. So, the property is that intersection belongs to, again, to our collection, to our base. And one more example is related to our integral sums, and that is about target partitions. So okay, example 2. May I read it? Example 2. Example 2. B is the set of B delta for delta positive, where B delta is the set of all target partitions such that the norm of partition is less than delta. So, why this is a base? Because look, if we take B delta 1 intersected with B delta 2, then once again that consists of all target partitions with minimum of delta 1 and delta 2. So you see, B delta consists of all target partitions. So you see, what is X here? X is the set of all target partitions. All target partitions. And as B delta, we took subsets which contains only partitions with norm less than delta. Then, what is I is a limit of a base of a function, f. What it means? It means, by definition, that for arbitrary epsilon greater than 0, there exists a B element of our base such that f of B is closer then epsilon to I. And look, this definition on base, works. For example, for usual limit. So, example 1. Limit of usual function. What it means? For arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x delta, f of x minus I less than epsilon. Now look, what is written here? There exists delta greater than 0 such that for all x, f of x is here. It's equivalent, look, that one. Remember, this was b delta, right? In example 1. Now example 2 of a base. Example 1 of a base, this was element of our base. In example 1, right? So, what is here? F of this element, image of every element of our set, is here, right? That is precisely what is written. Maybe that is bad thing. I should write like that, sorry. F of b is in the interval I minus epsilon, I plus epsilon. That is better, because that is a set of all f of x. I wrote in the wrong way. And example 2 is precisely what was written here. Look. Because now the limit of integral sums, look, what are integral sums? Let me write them down once again. Integral sum with fixed function f is a function of target partition. The function of target partition. And what was written as I equals to the limit as lambda of p tends to 0 as f p epsilon is precisely limit of a base of our function phi, where now base b is that one from example 2. Because now you see once again what it means. Look, there exists delta greater than 0, then every value of our function phi, that is function phi of our target partition, is in this interval. That is written precisely. So this idea of base unify all those limits, but I would say I don't think it's very necessary, and I'm not going to ask you limit over a base during an exam. So this was just for your information, let's say, for your information. But what is important, that is important. Definition of integral is important. Okay, and let me give a notation now. Finally, I can give the notation. So, once again, the notation. If the Riemann integral exists, of f over ab exists, then f is called integrable on AB, and the integral is denoted by integral from a to b f of x dx. And now I want to explain why this is, how to say, summation of uncountably many terms. Look, what is it? So, as we learned from definitions, right, we have, let me write down once again our definitions together in one form, short form. So, integral from a to b f of x dx equals to limit as the norm of partition tends to 0 of integral sums so look what happened, roughly speaking. So here we took finitely many terms like that. So we multiply a value of function at a point times length of small interval, right? Now lengths of those small intervals tend to 0. They become infinitely small. So we have infinitely small intervals. Multiply them by the corresponding values. And we sum them over all points of x over interval AB. So that is how we summarize uncountably many terms. Definitely we are not able to do it, right? How you can summarize uncountably many terms of this form. That is infinitely small, by the way, right? And we summarize all of them. How? That is the understanding of what is it. We take value of f at a point, multiply by small interval, small but finite, right? Non-zero. That is non-zero, right? And then we take a limit as those lengths tend to 0. You see? So that is why the sum is transformed into this integral, because it is a rather strange object, right? So what is this integral? You summarize uncountably many values of function f. Uncountably many, right? F of x is defined at every point of an interval. And we have uncountably many points on an interval, right? And we summarize terms of this form over uncountably many points, roughly speaking, right? And that is how we do it. We understand it like this limit. Liam? Of course, that is very important, I mean, to understand what is definition of the Riemann integral. So you should understand what is this limit in terms of epsilon delta, right? Without base. Don't need to do deeply into base, no. Just by usual epsilon delta language, and you should know target partitions and so on, right? Okay. Okay, and I have a couple minutes, maybe no, I think couple minutes is not enough. Instead of that, maybe it's good to no, for 2 minutes, what I can do for 2 minutes? Maybe a couple words about why Riemann 2n, Riemann integral. Why Riemann? In fact, now Riemann integral is not very good from the point of view of applications in theoretical things. Essentially better is Lebesgue integral. But for Lebesgue integral, roughly speaking, the idea is similar to Riemann integral, but in Riemann integral we split x-axis, right, to compute this area to make such rectangles. And in Lebesgue integral, the idea is different. We should split y-axis. So, and we need to compute as a sum of those horizontal figures. But you should understand that, for example, here it might be rather complicated, right? But nevertheless, it turns out that the idea to change x by y is very fruitful. It gives Lebesgue integral, which is better in many senses than Riemann integral. But to understand, of course, it's better to understand firstly Riemann integral and then Lebesgue. Okay, that's all for today.